All right, today we want to talk about the fundamental theorem of calculus, and the reason why it's called the fundamental theorem is because it ties together what was thought to be sort of two separate branches of the calculus, right? We've got differential calculus, which is concerned with the problem of finding a tangent line to a curve, and then we've got integral calculus, which is concerned with finding the area under a curve, say between two vertical lines. So those seem like two different things, but actually they're quite related. And so the point of the fundamental theorem of calculus is to show how they are related. In fact, in some sense, the derivative is the opposite of the integral. In fact, the integral can be thought of as an antiderivative. So here's what we need to look at first. Let f be a continuous function on the closed interval from a to b. And so now we'll let this capital F of x be the definite integral starting at a, stopping at x, of the function f of t dt. And again, I could have called this f of u du or f of r dr. You get the point. As long as these two things match, right, then we're good. So this is the accumulation function, and what it does is it tells you the area under the curve starting at a and stopping at x, right? We know the definite integral gives us the area bounded by the curve. So it doesn't go from a all the way to b, it just goes from a to x. And then we move x towards b, and what happens is you get more and more area as x moves closer to b. So you accumulate more area the farther away x gets from a. Unless, of course, the thing is below the x-axis, and then you start to add on negative areas. So let's look at a specific example of an accumulation function. All right, let's look at a graph of a particular function and then see what the accumulation function looks like. So here's a basic piecewise defined function, f, and it's got linear pieces, so we'll be able to compute the area pretty easily. So remember, capital F is the integral, the definite integral. In this case, we'll start at 0, and then we will stop at 5. So x can be anything between 0 and 5. Okay, so let's evaluate a couple points. So what's f of capital F of 1 then? Well, it's the integral from 0 to 1 of the function lowercase f. And remember, integral means area under the curve. So we want the area under the curve starting at 0 and stopping at 1. So it looks like, so you've got a square and a triangle. So you've got a 1, an area of 1, and then an area of 1/2. So it looks like capital F of 1 is 1.5. So basically, we just found the area of this region right here. And now what's f of 2? Well, f of 2 is start at 0 and then stop at 2. So now what's the area here? Well, we had the area 1.5 to here, and now we'll add an area of 2, so we accumulate a little more area as we move to the right. And so now this rectangle has an area of 2, so add that to 1.5, and you get 3.5. And now capital F of 3, that's the integral from 0 to 3. So that's the area under the curve from 0 to 3. So all we need to do now is to add the area of this triangle. So that's 1/2 the base times the height. So that's just going to be a 1. So now I know capital F of 3 is 4.5, and now f of 4. So now we've dipped below the x-axis, and so now we want to remove this area from our previous value, previous area. So now it's going to be 4.5, and then take away the area of this region here. So that's 4.5 minus 0.5, so here we get a 4. And now when we get to 5 finally, I'm going to remove yet another piece whose area is 1/2. So here I'm going to get a 3.5. So now let's see what this looks like. So f of 1 is 1.5. Well, first of all, what's capital F of 0? When I let x be equal to 0, the integral from 0 to 0, that's 0. Remember, when the limits of integration are the same, you get 0 area. So there's one good point. And then here we've got 1 comma 1.5, 2 comma 3.5, 3 comma 4.5, 4 comma 4, and then 5 comma 3.5. So that will look something like this. So here's a picture of the accumulation function. And now, what do we notice about capital F? Well, it looks like capital F is increasing from 0 to 3. That's exactly where this lowercase f is positive, from 0 to 3. And then it's decreasing from 3 to 5. That's exactly where lowercase f is negative. And remember, if the function is increasing, then its derivative is positive. And then when the function is decreasing, then its derivative is negative. So it looks like that the derivative of capital F is equal to lowercase f. And that's an important observation. Right, it looks like this this accumulation function is actually the antiderivative of lowercase f. And that is the main observation. That's what the fundamental theorem of calculus says.